Hello everyone. Today we are going to talk about the need for speed pruning transformers with one recipe. The motivation for this research stems from the need to improve efficiency in transformer design and its application in language and vision domains. Transformers have revolutionized deep learning, impacting various domains including natural language processing and vision-related tasks. However, their straightforward design, while enabling extensive applications, also brings a major drawback: high computational costs. This poses a significant challenge, especially in resource-constrained environments such as edge devices. In response to this, various state-of-the-art methods have been developed, including quantization, pruning, and knowledge distillation. These methods aim to address the computational bottleneck and have been explored in the context of convolutional neural networks, CNN compression. However, despite their success in compressing CNNs, these methods often encounter difficulties when applied to transformer architectures due to their unique structure. One of the key challenges is the massive size of transformer models. To address this, some works have introduced various methods of compression, which can be divided into one-shot and iterative. One-shot methods generally consist of a pruning phase followed by retraining to recover the lost generalization performance, while iterative processes account for the training dynamics and model compression. However, both methods have often been limited to a particular architecture task or required significant resources in the pruning and retraining processes. This leaves limited options for fast model compression that can be easily realized on standard hardware for different types of transformer architectures. The limitations of existing approaches and the lack of a general approach to transformer pruning across multiple tasks and modalities provide the motivation for the introduction of a unified framework. This led to the development of the One-shot Pruning Technique for Interchangeable Networks, OPTIN framework, which is designed to efficiently compress modern transformers. The novelty of OPTIN lies in its generalizability across domains and tasks, and its ability to produce competitive models without requiring retraining. This makes it a promising solution for future application to larger models across many tasks. The authors of the paper are addressing the problem of high computational costs associated with transformer architectures. This issue is significant because it poses a real impediment to the wide-scale adoption of these architectures, especially in resource-constrained environments such as edge devices. Previous methods to address this bottleneck, such as quantization, pruning, and knowledge distillation, have been explored, but these have often been limited to a particular architecture or task, or required significant resources in the pruning and retraining processes. The authors also highlight the lack of a general approach to transformer pruning across multiple tasks and modalities, which provides motivation for their work. They introduce the One-shot Pruning Technique for Interchangeable Networks, OPTIN framework, to efficiently compress modern transformers. The novelty of this framework lies in its generalizability across domains and tasks, and its ability to produce competitive models without requiring retraining. The OPTIN algorithm, which is part of this framework, computes and assigns importance to printable parameters and leverages the mask search algorithm from PTF to maximize scores in the partition search space. The policy partitions the search space by incrementally adding attention heads in order of importance, and at each step, adds the maximum number of rank-ordered neurons that will satisfy the cost constraint. This approach allows the step with the maximum cumulative importance to be considered optimal. The authors demonstrate the effectiveness of the OPTIN algorithm in maximizing scores in the partition search space, and show that the step with the maximum cumulative importance is optimal. They also show the versatility of the OPTIN framework across different domains and tasks. This work represents a significant contribution to the field, as it offers a solution to the problem of high computational costs in transformer architectures, and provides a generalizable approach to transformer pruning. Section 1. Problem formulation and approach. The authors have identified a significant challenge in the field of deep learning: the high computational costs associated with transformer architectures. These costs pose a barrier to the widespread adoption of transformers, particularly in resource-constrained environments. To address this issue, the authors have introduced the One-shot Pruning Technique for Interchangeable Networks, OPTIN framework. This framework is designed to efficiently compress modern transformers, making them more accessible for a variety of applications. Section 2. Methodology and experiment design. The OPTIN algorithm, a key component of the proposed framework, computes and assigns importance to printable parameters. It leverages the mask search algorithm from PTF to maximize scores in the partition search space. The search space is partitioned by incrementally adding attention heads in order of importance, and at each step, the maximum number of rank-ordered neurons that satisfy the cost constraint are added. The step with the maximum cumulative importance is considered optimal. This approach is unique in its ability to compress models without requiring retraining, a process that often incurs significant computational costs. Section 3. Improvements and innovations. The OPTIN framework represents a significant advancement in the field of transformer architectures. It is one of the first one-shot model compression techniques that can be applied across multiple tasks and architectures without the need for retraining. This makes it a highly versatile tool that can be used in a variety of domains. The authors have demonstrated the effectiveness of the OPTIN framework through extensive experiments, showing its robustness and generalizability across different tasks and architectures. This represents a major improvement over previous methods, which were often limited to a specific architecture or task. Technical results. The paper introduces the one-shot pruning technique for interchangeable networks OPTIN framework, which is a novel approach to efficiently compress modern transformers. The OPTIN framework is applied to natural language and vision-related tasks, demonstrating competitive performance with state-of-the-art methods in these cases. The primary contribution of the OPTIN framework is its ability to produce transformers with competitive performance at reduced computational loads across various task domains and architectures that can be realized on standard hardware. Key results and implications. The OPTIN framework's generalizability across domains and tasks is a significant result as it can produce competitive models without requiring retraining. This enables future application to larger models across many tasks. The framework's ability to maintain competitive compression rates without incurring the cost of retraining is another key result, which has implications for the wide-scale adoption of transformer architectures, especially in resource-constrained environments. The paper also demonstrates superior performance on a variety of tasks in language, vision, and application tasks, while maintaining competitive compression rates, without incurring the cost of retraining. Ablation studies and implications. While the paper does not provide specific ablation study results, it does execute several extensive experiments from framework-specific settings to applications on transfer learning and CNN networks. These experiments demonstrate the robustness and generalizability of the OPTIN framework over the task and architecture, which has implications for its potential use in a wide range of applications. Key highlights of the paper. 1. Key insights. The paper introduces the one-shot pruning technique for interchangeable networks OPTIN framework, a novel approach to efficiently compress modern transformers. It demonstrates the versatility of the OPTIN framework across different domains and tasks, including natural language processing and vision-related tasks. 2. Key contribution. The primary contribution of the paper is the OPTIN framework, which can produce transformers with competitive performance at reduced computational loads across various task domains and architectures. This framework can be realized on standard hardware, making it a practical solution for many applications. 3. Key idea. The OPTIN framework exploits the trajectory of prunable components in the transformer architecture to enable a smarter criterion for parameter selection. This allows for efficient compression of modern pre-trained transformer architectures without the need for retraining. 4. Key results. The paper demonstrates superior performance of the OPTIN framework on a variety of tasks in language and vision domains while maintaining competitive compression rates. It also shows robustness against compression rates and competitive performance against methods that perform retraining. 5. Key conclusion. The paper concludes that the OPTIN framework is a robust and efficient method for compressing transformer architectures. It shows promise for future application to larger models across many tasks, and the authors plan to explore more complex architectures and tasks in the future.